The impossible technology they erased from history. What if I told you there are ancient tool marks that match modern machining, but show up thousands of years early? 3 artifacts shatter timelines. A Greek gear computer sunk in a shipwreck, Egyptian granite cut like it met a power saw, and Indian metallurgy that shrugs at rust. Most people think it's myth or misread archaeology. But here, that's what actually happens when you test the claims. We're going to run every impossible artifact through a hard checklist: precision, power, materials, measurement, production, math. One number later will collapse the debate: repeatability. Let me show you how we'll separate legend from engineering. The checklist: what counts as impossible engineering? Okay, so here's the thing. Looks advanced isn't a metric. We need thresholds. Think of this as a pass-fail bench test for artifacts. If an object clears multiple categories at once, we're not looking at a fluke, we're looking at a system. First, precision. Not vibes, numbers. We're talking tolerances you can measure. Flatness, surfaces within tens of microns over hand-span distances, not just visually smooth. Parallelism and squareness. Deviations under 0.2 degrees across interior corners. Better yet, under 0.05 degrees on premium work. Circularity. Bores and cores with uniform diameter along depth and minimal taper. Consistent spiral pitch if rotary feed occurred. Symmetry. Matched components or paired faces that mirror within tight bands. Repeatability. Multiple objects from the same context showing near-identical dimensions. You don't hit those by accident, which brings us to power. Precision at scale demands controlled energy and motion. Rotary motion that's continuous, not just reciprocating scratches. Think wheels, drills, lathes, or water power. Sustained torque, enough to drive a saw kerf through hard stone or turn a large gear train without stalling. Energy storage and smoothing. Flywheels, water head, weight-driven regulators, or hydraulic buffering to even out pulses. Feed control, mechanisms that advance tools at steady rates, evident from uniform striation spacing or consistent tooth engagement. Next, materials science. The tool doesn't lie. Hardness relationships. Abrasives harder than the workpiece, corundum, emery, diamond, and evidence they were used systematically. Alloying and heat treatment. Phosphorus-rich irons, crucible steels, quenched and tempered edges or case-hardened surfaces. Microstructure. Slag stringers aligned by forging dendritic patterns from slow cooling, cementite networks in crucible steels. These aren't guesses, they're microscope visible. Wear patterns, polished wear on guides and jigs, not just decorative polish. Tool marks that suggest toothed profiles or abrasive-laden chords. Then metrology, the invisible backbone. If you see precision, somewhere there was measurement. Standards and gauges. Scribe lines at consistent offsets, master rods or cubit-like bars, possible surface plates, plumb and level indicators. Calibration footprints. Repeated dimensional families, widths or angles that cluster around specific targets. Layout logic. Center lines, reference faces, and datum strategies across assemblies. Mass production signals are the next tell. If one artisan pulled off a miracle, that's art. If 20 look the same, that's process. Jigs and templates. Identical radii, slot spacing, whole centers across dozens of pieces. Interchangeability. Lids that fit any box from a set, gears meshing beyond a single pair. Workflow marks. Sequential operations visible in the order of tool signatures, roughing, truing, finishing. Predictive math ties it together. You don't stumble into a differential by whittling. Gearing ratios that encode cycles, metonic, Saros, lunar anomalies, or mechanical advantages that land on rational fractions. Error budgets, evidence that builders understood cumulative error and compensated, like backlash control, escapement pacing, or indexing schemes. Astronomical or hydraulic modeling, mechanisms that anticipate flows, times, or alignments rather than merely display them. Now, how do we use this? Simple. For each artifact, we score across 6 domains. Precision thresholds hit or missed. Power source implied by marks and scale. Materials that make the toolpath plausible. Metrology evidence, standards and calibration traces. Production signals, repeatability across specimens. Predictive math encoded in function or design. A single pass doesn't prove a civilization had impossible tech. but 3 or more passes that reinforce each other. That's a workshop tradition backed by knowledge networks. You might be thinking, couldn't skilled hands alone do this? Skilled hands are part of the story. But here's where it gets interesting. Repeatability is the trapdoor. One masterpiece can be talent. Many near-identical masterpieces require fixtures, references, and controlled motion. That's what we'll test. We'll also watch for red flags. Polish equals precision mistakes. Gloss can hide waviness. We'll look at profiles, not reflections. Tool mark ambiguity. Random scratches won't cut it. We need uniform pitch, kerf width consistency, or tooth signatures. Overreach claims, like nanotechnology when surface roughness says otherwise. And we'll accept limits. Some objects might pass 2 categories and stall on the 3rd due to missing data. That's fine. We'll tag them promising but unproven and propose tests. 3D scans, profilometry, SEM residue analysis, and constrained replications using period-consistent tools with documented time and labor. One more thing before we apply the list. Energy density caps ancient workshops, but clever mechanisms multiply limited power. Waterhead becomes rotary motion. Gravity becomes regulated ticks. Abrasives become cutting edges. When those tricks show up alongside precise measurement culture, you get results that look impossible until you measure how they were achieved. So, checklist locked. Next, we put the Antikythera Mechanism on the bench and see how many boxes it really ticks. Antikythera Mechanism, analog computer before computers. Most people have heard the headline, Ancient Greek Computer Found in a Shipwreck. But here's what actually shows up once you scan it. Radiography and CT slices reveal a stack of bronze plates packed with intermeshing gears, 30+ depending on fragment counts, each cut with fine triangular teeth. Inscriptions wrap around the device like a user manual. These aren't decorative glyphs, they're labels for cycles, Metonic, Callippic, Saros, and Exeligmos, plus named games like the Olympics. When you rebuild those trains from the CT data, the ratios encode lunar months, eclipse seasons, even the moon's anomaly. It's speed up and slow down across the sky. Now the checklist. Precision first. Tooth counts aren't random. They land on purposeful integers that multiply into those astronomical cycles. That means center distances, tooth profiles, and plate spacing had to be controlled well enough to avoid jamming. CT reconstructions show gear centers located by riveted or peened pins with consistent offsets. The teeth are worn but regular, implying a repeatable pitch. You don't get gear trains to mesh over multiple stages without keeping tolerances within a small fraction of a tooth pitch. Is it Swiss clock tight? No, but it clears the bar for functional precision. Power and motion. There's no battery here, just human input. A hand crank or knob turns the main drive shaft and everything else cascades. But here's the subtlety. You can't turn 30 gears smoothly by brute force if friction spikes all over the place. The surviving bearings are simple holes, yet the designers distributed load across multiple plates, reducing shaft bending and helping alignment. We also see dial trains that amplify tiny angular errors into readable outputs. That means the feed, the rotation you put in, had to be steady enough that the dials didn't chatter. In practice, a knob, a light oil, and careful clearances smooth it out. No watermill needed. Consistent human rotary motion is enough for a display machine. Materials, bronze on bronze can seize, but with tin content tuned and a touch of lead, you get machinability and decent bearing behavior. The tool marks visible on some fragments suggest hand filing and possibly saw-cut blanking before tooth shaping. Were abrasives used? Almost certainly. Emery was known in the Aegean. The combination matters. A workable bronze, abrasive finishing, and thin plates riveted to a frame give you a lightweight but stiff assembly that survives moderate torsion. Metrology next. This is where the device screams workshop culture. Inscriptions include scale divisions, month names, and eclipse prediction glyphs with Greek letters keyed to tablets of corrections. That implies a standard for angle division, regular spacing across a dial, plus a way to mark and check. You don't scribe 235 divisions around a ring metonic by eyeballing, you index. Whether by a primitive dividing plate, a toothed reference wheel, or a templated compass step, the layout logic is there. Center lines, datums, layered subassemblies that locate on one another with predictable offsets. Even the handwriting density hints at a bench routine. Design first, label later, assemble to marks. Mass production signals? We don't have a room full of these, so interchangeable parts are tough to prove. But there are hints of repeatable practice. Some gear modules, the tooth size relative to diameter, appear reused across different wheels, which suggests standard cutters or files and a known pitch. The box architecture shows a consistent plate thickness, likely from hammered sheet brought to gauge. And the inscriptions refer to functions that would be meaningful to any literate user in that tradition, suggesting this wasn't a one-off magic trick, but the top end of a line. Predictive math is the slam dunk. Differential gearing shows up in reconstructions of the lunar display. A clever train subtracts two motions to simulate the moon's variable speed. That's not mystical, it's mechanical math. Ratios like 223 for the Ceros and 19 for the Metonic are encoded by tooth counts. Builders understood cumulative error enough to include correction glyphs and a 4 Ceros exeligmos cycle to handle drift. You're not just displaying time that already passed, you're projecting future eclipses, which requires a model, however simplified. Manufacturing difficulty. Tooth profiles look closer to cycloidalish flats than later involutes, cut by hand with files and guided by scribed lines. The challenge isn't one tooth, it's the repeatability across a ring. A modern machinist who tries to replicate the mechanism with only period-plausible tools discovers the pinch point, indexing. If your spacing drifts, the gear binds by stage 3. Micro story, a watchmaker I spoke with tried a 27-tooth wheel using only a hand-scribed index and a file. The first version walked a degree off by the end, useless. On the second attempt, he made a crude dividing plate with punched marks and a detent spring. Suddenly, the teeth landed within a sliver and the train ran. That's the power of metrology, not magic. So how many boxes does Antikythera tick? Precision, pass functional grade. Power, pass human rotary with friction management. Materials, pass bronze and abrasives used intelligently. Metrology, strong pass, indexing, scale division, labeling logic. Production, partial pass, standards implied but sample size small. Predictive math, hard pass, ratios, anomaly modeling, error handling. Why this matters isn't the gadget count, it's the workshop behind it. A device like this implies jigs we haven't found, wooden fixtures long gone, and a culture that valued calibration. It also reframes isolated genius. Yes, a brilliant designer likely led the project, but the fabricators still needed shared techniques, sheet thickness control, repeatable drilling, and a way to keep shafts square to plates. That's a network. And once you see that network at play in bronze and gears, you can't unsee it when we jump to stone. Because if Greece could encode the sky into ratios and teeth, what were Egypt's workshops encoding into granite, flatness, parallelism, and motion, where the tools don't survive but the surfaces do? Egyptian Aswan granite, drill cores and saw marks. Everything changes when you leave bronze gears and confront granite. Aswan granite is quartz-rich, around Mo 6-7, and it punishes sloppy tooling. Yet across Egypt, you see surfaces and marks that behave like controlled rotary machining, not random abrasion. Let me show you what to look for, and we'll run the checklist as we go. Start with the infamous drill cores. In museum drawers and old excavation photos, you'll see cylindrical cores and matching holes with helical striations wrapping down the wall. Most people think, okay, sand and a stick. But here's what actually matters, the pitch and uniformity of those spirals. On several cores, the grooves maintain a near-constant lead, meaning the bit advanced at a steady rate per revolution. That's a feed. Abrasive slurry can cut, sure, but a stable, repeating pitch suggests a guided tubular drill with consistent downforce while rotating. Our power category asks for continuous rotary motion and feed control. Uniform helical striations are the receipt. Now the tool question. Copper alone can't outhard quartz, but copper carrying corundum or quartz abrasive absolutely can. That's Materials Science 101. The abrasive is the cutter, the tube is the carrier. You'll also see ridges corresponding to the rim of a hollow drill, thicker at the edge, lighter inboard, as if the cutting action concentrates on a narrow annulus. That pattern matches a tubular crown with slurry replenished as it cuts. If the pitch tightens or loosens, you're seeing the operator adjust pressure or the slurry thicken. When multiple cores from the same context share similar diameter, kerf signature, and pitch, we're stepping into repeatability, our open-loop measurement coming into focus. Shift to saw marks. On quarried Aswan blocks and partially finished slabs, kerf lines run parallel with widths that cluster around specific bands, often a few millimeters, too consistent to be random hand sawing with a wandering blade. Hypothesis 1, a large reciprocating saw frame charged with abrasive. Hypothesis 2, a continuous loop saw, or even a large diameter rotary saw with an abrasive edge. We're not smuggling in carbide. We're asking if a mass-bearing device delivered steady, straight motion. Long, straight kerfs with constant width imply guided alignment and a regular stroke. Feed control again. If the kerf curves slightly at the start and steadies, that looks like the moment a heavy frame settled into a guide. Flatness and right angles are the brutal test. The interiors of some granite coffers and sarcophagi show surfaces that read flat beyond a visual gloss. When you put a straight edge and feeler gauge across the interior, deviations can be surprisingly tight over long runs. External corners approach true right angles with minimal light leakage against a good square. One-off virtuosity. Maybe until you measure multiple faces and find consistent parallelism and squareness within small fractions of a degree. That's metrology footprints, reference faces, layout lines, and likely the use of abrasive lapped surface plates in wood or stone that didn't survive. Okay, so what about power density? Do you need a watermill under Giza? Not necessarily. A bow or strap drill can produce rotary motion. A weighted drill press with a bow can regulate downforce. Teams can drive large framed saws. Add flywheel-like inertia in a heavy saw frame and you smooth the stroke. If you suspect tubular drills, look for concentricity, holes staying on axis, minimal wandering. That implies guides, jigs that start and keep the tool centered. Jigs are mass production signals. You also find repeated hole diameters across sites, clustering around families of sizes, another hint of standardized tooling. Counter-argument time. Abrasive slurry explains everything. It explains cutting power, yes, but it doesn't explain uniform striation pitch across depth unless motion and feed were controlled. Skilled artisans know machines. Skilled, absolutely. But skilled artisans invent fixtures when work gets hard. That's the step from art to process, and it leaves signatures. Micro story. An engineering professor brought a contact profilometer and a granite straightedge into a seldom measured chamber. He sampled an interior surface every 50 millimeters, recorded roughness and waviness, and mapped the deviation. The surface wasn't glass smooth. It showed low amplitude, long wavelength flatness with short wavelength polish, in other words, a trued plane with a finished skin. The orthogonality check on adjacent faces landed inside a tight band, better than a rough-hewn box by orders of magnitude. His reaction: this is shop logic in stone. Let's score the checklist. Precision, strong indicators, flatness, parallelism, repeatable kerf widths, and bore circularity with consistent pitch. Power, pass in principle, reciprocating saw frames, rotary tubular drills, weighted feeds, no fantasy energy needed. Materials, pass, abrasive-laden copper and sand corundum slurries match the marks. Metrology, pass, layout lines, consistent angles, and implied surface reference practice. Production signals, partial to strong, clustered diameters and repeated kerf widths point to standardized tools and jigs. Predictive math, light mechanisms don't encode ratios, but the regular feed rates hint at tacit process control. Why it matters? Granite remembers motion. Tool marks and planes are the black box data recorder of a vanished workshop. If repeatable helical feeds and constant kerfs persist across sites and eras, the debate collapses onto one word: repeatability. Not a single miracle, but a practice system. And once you accept guided rotary drilling and framed sawing in abrasive regimes, the leap to industrial-scale stone shaping stops being impossible. It becomes a question of logistics, teams, jigs, guides, and time, which is exactly where we're headed next. The Serapeum boxes, precision at massive scale. From guided drills in granite to objects that feel like they were built inside a machine shop, the Serapeum boxes are where the argument gets loud. Deep under Saqqara in tight corridors sit black granite and hard as nails diorite coffers the size of cars. If precision is hard, scale makes it brutal. So we'll run the checklist and see if these aren't just impressive but systematic. Start with what your eyes can't fake: fit and geometry. Box and lid interfaces show contact along long stretches, not just at a few proud points. When researchers put straightedges across the lips, light leakage is minimal over broad spans. Corners red square to a degree that implies intentional truing of reference faces. Internals aren't just smoothed, they're trued, flat planes that meet at orthogonal angles, with polish consistent into corners rather than only on the easy open faces. That's crucial. Polishing alone creates shine. It doesn't create flatness that holds across meters. Surface finish tells a story too. On several interiors and lids, you see directional burnish patterns that run true and parallel, suggesting a repeated finishing stroke guided by a reference. Exterior long faces exhibit parallelism better than you'd expect from hammer and chisel alone, and chamfers are cut with stable angles along entire edges. When you map these features across multiple boxes, the numbers cluster. That's our open-loop closing, repeatability at massive scale. Now logistics. You don't quarry, dress, and position blocks like this without planning. The quarry source for many is Aswan, hundreds of kilometers away. Each block likely left the quarry oversized, then was trued in stages, roughing, squaring to references, hollowing, and finishing. Moving them through desert onto boats and into a cramped underground gallery means you plan orientation long before the final polish. The tunnel geometry itself is telling: tight turns, narrow passages. That implies the lids and boxes were finished largely before placement, because machining in that space would be punishing. So how did they keep alignment and preserve those fits after transport? The simplest answer is metrology: reference marks, datums on edges, and final lapping of contact bands once in situ. Tooling signatures push us toward controlled motion. On interior walls, faint, evenly spaced streaks align, as if a flat tool charged with abrasive traversed in guided passes. In cavities, the regularity of the surfaces argues for a repeated stroke length with overlap, classic workflow marks, roughing grooves smoothed by longer, lighter finishing passes. You also find polish concentrated where lids and boxes meet, with a surface sheen distinct from decorative faces. That's a functional contact surface, an engineered interface, not just a pretty skin. Energy budget next. Could manpower alone do this? Yes, but raw force without control doesn't yield these tolerances. Think teams driving large, stiff abrading tools, sled-like laps, long planers, and framed saws charged with emery or quartz. Add weight for downforce, guides for straightness, and slurry management to maintain cut rate. The power is gravity and bodies multiplied by jigs. Flywheel effects show up at scale too. A heavy lapping beam has inertia that smooths hand variability, the same way a big saw frame stabilizes a stroke. On the hollowing question, you can combine tubular crown drilling to remove bulk with chisel and abrasive planing to true interiors. The flatness says something like that happened. Mass production signals matter most here. Across the vault, dimensions fall into families, box widths and heights that repeat within tight bands rather than random spreads. Lid rabbits show consistent depths and angles. If one lid mates to its box with high area contact, that's craftsmanship. If many do with similar geometry features, you're staring at a process, templates, gauges, and fixed tooling widths. Interchangeability across boxes isn't claimed, but the family resemblance screams standardization. Metrology footprints are subtle but persistent. Scribe lines near edges at consistent offsets. Occasional layout remnants on non-show surfaces. You don't maintain orthogonality in meters of granite without some form of reference plane, likely flat stones or metal-studded wooden plates lost to time, recharged with abrasive and checked with straight edges and plumbs. The tunnels level benches and locating shoulders read like fixtures. You set the box to a datum, then do the last touch on the contact band to lock alignment. Functions: the mainstream answer is Apis bull burials, and some boxes contained remains. But function doesn't change fabrication reality. If it's ritual, the logistics are still industrial: quarry scheduling, crew rotation, tool life management, and a supply chain of abrasives, oil, and sleds. If anyone claims they polished it, ask, then why do interior planes read as trued flats, and why do lid fits distribute contact so evenly? That's not ceremonial randomness, that's engineering intent. Skeptics point to chisel marks on some faces and say, see, handwork. Of course, chisel's rough. The question is whether the finish and geometry exceed what unguided chiseling yields. Our checklist says yes, the repeatable flatness, parallelism, and interface quality cross the precision threshold. Power, pass mechanized by mass and guides, not magic. Materials, pass abrasives against granite, copper carriers, stone laps. Metrology, strong pass, layout, and datum logic. Production. Pass, dimensional families and process signatures. Predictive math, light. But we do see process control in consistent stroke artifacts and contact band widths. Here's the micro-story payoff. A modern stone shop tried to duplicate a scaled Serapeum-style lid fit using only abrasive-charged tools and wooden laps. No diamond blades, no powered grinders. They built a sled lap, weighted it, ran guided strokes, and blue-checked contact with pigment. The first hour looked awful. By the second day, the contact band expanded and evened out. By day 4, they had a lid that seated with air cushion resistance over a high-area fit. Their conclusion: the hard part isn't force, it's reference. Once the datum was stable, progress was inevitable. That's the point. These boxes aren't impossible, they're unforgiving. And the marks say the builders had a measurement culture strong enough to tame unforgiving stone at massive scale. Now, if Egypt demonstrates metrology in rock, what happens when a civilization turns that same discipline on metal itself? India's iron pillar and lost zinc distillation. If stone tells you how clean their measurement was, India's metals tell you how deep their process knowledge ran. Start with the thing tourists tap and scientists sample, the Delhi iron pillar. It's over 1,600 years old, made from forge-welded blooms, and it refuses to rot in open air. People call it rust-free. That's not quite right. It rusted once, then it stopped. Here's what actually happened. The pillar's iron is phosphorus-rich and relatively low in sulfur and manganese, typical of bloomery smelting with certain Indian ores and charcoal. That chemistry matters. Over decades, a thin, adherent layer formed on the surface, a complex iron hydrogen phosphate hydrate with hematite, what corrosion engineers call a passive film. Think of it as a self-limiting glaze. Instead of flaking like red rust, it bonds and seals. Monsoon wetting cycles help the film mature. Delhi's atmosphere, with low chlorides and enough humidity to grow but not spoil the layer, did the rest. Metallography shows slag stringers and inclusions aligned by forging. Those inclusions aren't defects here. They're micro-reservoirs for phosphorus that feed the passive film at the interface. In the checklist, that's materials science and process control working together. Precision, not microns. But the pillar passes a different test: repeatability of process at large section sizes. The weld lines, the consistency of bloom consolidation, the straightness over height, all point to controlled forging heats and jigs that kept the column true. Power is human and charcoal-fueled furnaces, but the metrology shows up in the alignment and plumb. The real value is the stable outcome, corrosion rate that drops to near zero once the film forms. That's engineered durability by composition, not by coating. Now pivot to India's other metallurgical ace, Crucible steel, the Wootz tradition. Inside sealed crucibles, iron plus carbon-bearing materials were heated to a fully liquid or near-liquid state, then cooled to develop a network of cementite within a ferrite-pearlite matrix. When forged intelligently, you get incredible edge holding and a distinctive watered pattern downstream in Damascus blades. Under a microscope, you see aligned carbides, controlled segregation, and a story of temperature discipline. This is predictive process. You don't get that pattern without stabilizing the melt chemistry, the soak time, and the cooling rate. Checklist hits, materials pass with distinction. Predictive math, implicit in the control of phase transformations and heatwork cycles. Production signals, standardized crucible shapes, charge recipes, and workshop traditions passed across regions. But the case that nails industrial thinking long before industry is zinc. Most metals you smelt condense as solids or stay in the pot. Zinc evaporates around 907 degrees C and will burn to oxide in air. To collect it, you need a distillation system that separates vapor from oxygen and condenses it on a cool surface. At Zawar in Rajasthan, archaeological surveys found exactly that. Long galleries, banks of ceramic retorts set at angles, with condensers and channels to collect liquid zinc. Hundreds, even thousands of retorts in batch arrays suggest scaled production, not experiments. Process knowledge is written into the hardware. Retorts show vitrification consistent with sustained high temperatures. Condensation galleries have residues that match zinc oxide and metallic zinc traces. Airflow management features reduce oxygen ingress. Temperature control? Look at chimney design, firing tunnels, and the thermal mass around the retort banks. These smooth heat pulses and keep the vapor stream steady. Oxygen management shows up in seals, clay luting, and the orientation of retorts so vapor flows one way, fresh combustion gases another. That's power, metrology, and predictive math rolled into a furnace hall, heat budgets, draft control, and timing. Industrial organization sits behind it. Mining, ore dressing, charcoal logistics, clay body recipes for retorts, standardized vessel dimensions so the racks fit and the seals work. You don't get 1,000 identical tubes by chance. That's jig thinking. It's also repeatability. Failure rates in retorts drop when wall thickness and firing profiles stabilize. Archaeologists map broken retorts and see consistent sizes cluster in tight bands. There's your open loop number again. What would zinc enable? brass made deliberately, not accidentally. With metallic zinc on hand, you can produce uniform brass by controlled cementation or direct alloying, landing on mechanical properties within a predictable range. Decorative uniformity isn't just pretty, it's process stability. Corrosion behavior benefits too. And in electrochemistry, ancient batteries are debated, but plating is clearly easier when you understand how to produce consistent alloys and manage oxides. Even without electricity claims, a zinc economy changes toolkits. At score, precision, not micrometers, but dimensional control in crucibles and retorts says pass at the process scale. Power, charcoal furnaces, draft systems, and batch arrays pass. Materials, hard pass, phosphorus-rich iron, crucible, steel microstructures, metallic zinc production. Metrology, pass, standardized vessel sizes, repeatable wall thickness, firing cycles inferred from residue gradients. Production signals, hard pass, mass retort farms, supply chains, interchangeable racks. Predictive math, pass, phase behavior understood in practice, vapor pressure realities solved by apparatus. Microstory. A modern ceramics lab replicated a Zauer-style retort with locally plausible clay, set at the historical angle, sealed with ash-lime luting. They charged calamine ore and charcoal, fired on a rising curve held, then let the system breathe through a narrow draft. Condensate formed as gray crust, then droplets of zinc in the cooler zone. The first run cracked the retort. The second, with a thicker shoulder and slower heat ramp, survived and yielded more metal. Their takeaway? The ancient layout is a control system in bricks. Tie it back to our throughline. The iron pillar's passivating skin isn't a miracle, its composition turned into performance through environment. Wootz isn't magic steel, its thermal schedules encoded in craft. Zauer isn't rumor, its distillation scaled by metrology and logistics. When you see the same pattern, measure, standardize, repeat, across metals and stone, impossible stops being a mystery and becomes a missed syllabus. Now let's test the electricity claim everyone argues about, the Baghdad batteries, and what the checklist says they can or can't do. The Baghdad batteries and Parthian electrochemistry debate. You've seen metals and heat mapped to standards. Now let's stress test the electricity story everyone cites, the so-called Baghdad batteries. Here's what we actually have: a small ceramic jar, a rolled copper cylinder inside, an iron rod centered within the copper, bitumen sealing the top. These show up in the Parthian Sasanian layers around Kujet Rabu. No wires, no switches, no light bulbs, just a vessel, two dissimilar metals, and a seal. Could it produce voltage? Yes, if you add an electrolyte like vinegar, grape juice, or lemony tartar. Lab tests with replicas routinely show between 0.5 and 1 volt per jar. String a handful in series and you can hit a few volts. That's enough for a tingling sensation or low-rate plating DMOS. Researchers have plated thin films of copper or silver onto small objects with battery chains, so the physics checks out. But the question isn't, can it work? Did they actually use it that way? Run the checklist. Precision. The copper cylinder is neatly formed, the iron fits inside, and the bitumen cap seals well enough to prevent evaporation. Not micrometer work, but sufficient fit for a cell. Power. This is chemical, not mechanical. Single cells deliver tiny current, milliamps at best. So if this was a power source, we'd expect banks of jars and evidence of bus bars or tie wires. That's the first bottleneck. We don't find racks of deliberately connected cells or cable hardware in situ. Materials science, clear pass on the ingredients. Copper and iron form a galvanic pair. Bitumen is a competent sealant. Ceramic is electrically insulating and acid-resistant enough for weak electrolytes. We even find residue in some jars that tests acidic or wine-like in replications, though the original vessels don't preserve definitive electrolyte fingerprints. Metrology, light signals. The jar dimensions vary. There's no obvious standardized neck diameter to accept a common stopper geometry that screams battery module. However, the repeatable copper-iron bitumen stack suggests a template for assembly. Production signals are where the story falters. If electroplating was a workshop routine, we'd expect telltales. Consistent plating thickness across many artifacts, underlayer adhesion patterns, and bath-related defects. Runs near edges, thin coverage in recesses. Most ancient plated items in the region are fire-gilded or mercury amalgam treated from later periods, or their diffusion cementation brass, no battery needed. A few museum pieces with mysterious plating haven't held up under modern cross-sections. They're surface-enriched or leaf-applied. Predictive math? Minimal. Battery arrays need series parallel planning to hit target voltage current for a task. We don't see notch stoppers, polarity marks, or layout scribes that indicate systematic electrical design. No inscriptions listing counts or duty cycles. If a craft depended on cells, the process control would leave instructions, or at least recurring fixtures. So what's a plausible function? 3 candidates get airtime. 1. Ritual or therapeutic devices, small shocks as healing. Maybe, but that's speculation without texts. 2. Quick and dirty electroplating for accents on small jewelry, physically possible, but the archaeological record lacks consistent plating signatures and cabling hardware. 3. Storage for scrolls, incense, or papyrus with the metal parts serving a non-electrical purpose. The battery look is incidental. That's boring, but it fits the absence of electrical infrastructure. Micro story. A conservator tried an 8-jar series using wine vinegar. Voltage, 6.8 V open circuit current, under 1 mA through a small cathode. They plated a whisper of copper onto a silver bead in 90 minutes. Looked decent wet, patchy once rinsed. After 2 days, cells dried out, iron corroded, and bitumen cracked. Verdict, workable demonstration, terrible production method unless you stabilize seals, replace electrolytes, and manage leads, all of which would leave hardware traces. Checklist verdict, precision, pass for functional fits. Power, weak pass, capable but low density, no arrays found. Materials, pass, correct galvanic pair and sealant. Metrology, partial repeatable assembly, little evidence of electrical standardization. Production, fail to partial, no racks, leads, or widespread plating diagnostics. Predictive math, fail, no serial planning footprints. What would count as a smoking gun? A bench of jars with metallic tie wires fixed in series, residue mapping of sulfate or acetate ions consistent with battery use, and a pile of uniformly plated artifacts with cross-section proofs. Short of that, the conservative call is proto-electrochemistry plausibly known, industrial use unproven. So where does that leave our pattern? Electricity remains a maybe. But gears, hydraulics, thermals, abrasives, and metrology already clear the bar across cultures. And our open loop, repeatability, still rules. Without repeatable arrays and outputs, the battery claim stays a curiosity, not a system. Chinese Han-era gears, water clocks, and south-pointing Chariot. You've seen abrasives and metallurgy carry the load. Now watch what happens when a bureaucracy obsessed with calendars and taxes points that mindset at regulated motion. In Han and after, China doesn't flirt with precision. They institutionalize it. Start with gearing you can hold. Chinese odometers are described in court texts. A cart whose wheels turned a gear train that dropped pellets or hit a drum at every li. That's not legend. It's a ratio problem solved with wood and bronze gear sets sized to road wheels. You're encoding distance into discrete ticks. Checklist time. Precision. Tooth counts and center distances must repeat or the count drifts per mile. Power. The road drives the train, constant rotary motion. Materials. Hardwood frames, bronze pins, old bearings, and lacquer to stabilize moisture. Metrology. A standardized li and wheel diameter. Production. Multiple carts for imperial roads, repeatable builds. Predictive math. Gear ratios translating circumference to counts. That's a full stack pass in a rolling box. Armillary spheres take it vertical. Han-era astronomers build nested bronze rings geared to track celestial motion. Later, the differential armillary by Zhang Heng and improved in Song times ties ring motion to a single drive. When you couple rings, any backlash or eccentric center shows up as wobble. So they cast bronze with tight fits, lap pivots, and index divisions with consistent spacing. The same measurement culture that carved calendar stones now lays out degree marks around circles. You can see the bench logic. Reference axis, scribed graduations, and standardized ring widths so pointers clear without rubbing. Again, ratios matter. Sidereal day, solar year, encoded in gear trains or water-driven drives downstream. Which brings us to the water clock, where everything we've talked about, power smoothing, feed control, error budgets, goes literal. A clepsydra drips, yes, but a Han or Song clock regulates. You control head height so flow stays steady. You add float regulators that translate water level to rotary motion. You introduce an escapement-like device, wooden predecessors to later verge mechanisms, to tick evenly. The text tradition credits Yi Xing and Liang Lingzhen in Tang with an early escapement concept, and Su Song in Song with a full tower clock. Water wheel, scoop buckets, escapement, gear trains, and celestial displays. Even if some reconstructions argue details, the system logic is unmissable. And the checklist. Precision. Wheel buckets and teeth must be uniform or the rate wanders. Power, gravitational waterhead buffered by tanks, smoothed by the inertia of a large wheel. Materials, bronze axles, hardwood frames, well-fired clay pipes, and carefully sealed joinery. Metrology, graduated scoops, calibrated drips, and dial divisions for hours and quarters. Production, tower clocks require teams, manuals, and maintenance schedules. Cold season flow adjustments, sediment management. Predictive math, designers compute gear ratios to turn day length into dial rotation, and they compensate for seasonal flow changes with head tanks and weirs. That's predictive control, not passive flow. There's also the south-pointing Chariot, the device everyone cites, usually with a wink. Legend says it always points south without magnetism, predating the compass. Mechanically, the plausible version is a differential. As the cart turns left or right, a gear train subtracts wheel rotations and rotates a pointer to compensate. If you gear it right, the pointer maintains heading. Does it work over long distances? Only if wheel slip is minimal and gear lash is tight. In practice, it's a demonstration-grade device on good roads, but the technology underpinning it, the differential, is real. You can model it with wooden gears, and Chinese technologists clearly understood wheel right versus wheel left subtraction. Even if the Chariot was ceremonial, the differential concept is a design jewel. Bronze casting is the quiet enabler. Chinese foundries cast complex forms with piece mold techniques that deliver near-net shapes. Precision improves when molds reference master patterns. Repeatable thickness, consistent hub bores. Those bores then get reamed and lapped. Standardized components show up everywhere. Axle caps, pin sizes, and latch geometries that interchange. Bureaucracy rewards that habit. If you can ship a part from one workshop to another and it fits, the empire runs quieter. Documentation seals the case. Technical manuals, later codified in song texts like Shen Qiu's Dream Pool Essays and Su Song's Clock Treatise, record problems and fixes, tooth wear, water freezing, float drift. Earlier hand sources emphasize calendrical reforms anchored by observation instruments, which implies maintenance of accuracy, not just initial construction. That's metrology culture writing to itself. Court workshops become knowledge hubs, with master patterns, tool chests, and apprentices learning how to file a tooth to pitch rather than to eyeball. Micro story. A modern carpentry team built a small water wheel with bucketan pallet regulation based on song diagrams, using only hand tools. Day 1, the wheel surged fast, slow, fast as buckets filled unevenly. Day 2, they shaved each bucket to weight match within a few grams, added a header tank to hold constant head, and polished pivot pins with oil. The rate settled within a narrow band. The dial tracked noon to noon within a few minutes. Their takeaway? The secret isn't a magical escapement, it's tolerance stacks managed by measurement. Score it: precision, consistent tooth pitch, dial graduations, and float response, pass. Power, waterhead into regulated ticks, pass with elegant smoothing. Materials: bronze, hardwood, lacquer, ceramic, pass. Metrology: heavy pass, unit standards, degree divisions, manuals. Production: pass, court workshops, and repeated builds. Predictive math: hard pass, ratios, differentials, calendar cycles computed into hardware. Once you see it, the pattern rhymes with Greece and Egypt. Controlled motion, encoded ratios, and a paper trail of maintenance. The difference is scale of adoption. In China, the state keeps the bench alive for centuries. And that's what we'll need in the next stop, where precision hides in city grids, canals, and stone that fractures like glass. Mesoamerican stonework and Teotihuacan city-scale engineering. You probably think precision lives in gears and gauges. But what if a whole city is the machine? Teotihuacan is where measurement culture moves from benches to boulevards, and the tool marks are streets, canals, and stone blades by the million. Start with the grid. The city isn't random sprawl. It's locked to a fixed azimuth, about 15.5 degrees east of true north, across avenues, compounds, and pyramids. That's not close enough. Blocks repeat with a module that recurs site-wide, which means surveyors carried standards, transferred them with sighting rods, and checked drift over kilometers. The Avenue of the Dead holds alignment across long sightlines, suggesting a datum line established early and protected through phases of construction. If you've ever tried to keep a chalk line straight for 30 meters, you know the drift problem. Multiply that by 1,000, and you start seeing the metrology behind the view. Hydraulics next. Teotihuacan sits in a basin where water is either not enough or way too much seasonally. Archaeologists map channels, sluices, and basins in and around the ceremonial core and residential barrios. Cut channels show stable slopes, gentle but intentional, so flow runs without gouging. Where channels step, drop structures calm water. That's hydraulic regulation baked into masonry. You also see maintenance logic. Sediment catch points with access, bypasses that let crews service sections without shutting a whole line. Our checklist loves that. Predictive control, not just reaction. The pyramids themselves show another kind of engineering, thermal and acoustic behavior. Hand clap in front of the Pyramid of the Moon or at Chichen Itza and you'll hear a chirp-like echo. At Teotihuacan, plazas and staircases bounce sound in focused ways. Was that an accident? Maybe sometimes. But repeated geometries, stepped faces, and plaza proportions that amplify voice to crowds hint at intentional performance. On hot days, shaded galleries and stone mass store and release heat, smoothing temperature swings. Even if they didn't solve wave equations, they learned by iteration. Build, observe, adjust. That's experimental archaeology in real time. Stone shaping here isn't granite elegance, it's basalt and andesite discipline. Basalt is tough and andesite fractures unpredictably. Workshops at Teotihuacan turned that constraint into a product line, prismatic obsidian blades. Obsidian is volcanic glass, brittle but capable of edges finer than surgical steel. The trick is platform prep and percussion angles. The city scaled it. Debitage piles show standardized flakes, uniform widths, and an economy of motion that screams jigs and craft routines. If thousands of blades per day leave workshops with consistent cross-sections, repeatability is the ruling number again. Not microns, but tolerances that let a blade haft into standard handles without wobble. Look at masonry seams. In retaining walls and platforms, you'll find courses that hold line across long runs with joints that neither drift wide nor pinch tight. Stones often show percussion dressing on faces and abrasion on contact surfaces. A mixed toolkit like we saw in Egypt, but tuned to available rock. Kerf-like grooves on some blocks suggest chord abrasion used to true edges. The kerf width clusters around narrow bands, which hints at chord diameter families, standard tools, not random rope. Production isn't just in stone, it's in people. Teotihuacan's barrios specialize, pottery here, obsidian there, shell and pigment elsewhere. That's supply chain. It means roads sized for loads, waypoints, and scheduled discipline. To keep the grid clean while compounds build and rebuild, you need survey resets, re-establish the line, re-square the block, tie new work to the old datum. Think of a city-wide jig you keep checking against. Astronomy runs through it. The main axis aligns with certain horizon events. Plaza orientations capture solar angles on key dates. Watch shadows rake a staircase and you get a calendar signal. This isn't horoscope aesthetics, it's predictive math embodied in masonry. If you can count interval days between shadow events across seasons, you can schedule plantings, festivals, and tax cycles. The architecture becomes a regulator. So checklist time, precision. Pass azimuth control across kilometers, repeating modules, standardized stone interfaces. Power, pass gravity in channels, human transport optimized by grid and production lines in workshops. Materials, pass obsidian fracture mechanics mastered, basalt dressed with percussion and abrasion. Metrology, strong pass, survey standards, slope control, and astronomical indexing. Production, hard pass, industrial obsidian output, modular urban construction, specialized barrios feeding central works. Predictive math, pass, calendar signals in alignments and plaza geometries, hydraulics tuned to gradient and flow. Microstory, a field team laid a modern total station along the Avenue of the Dead, shooting points every 25 meters. Over a kilometer, lateral deviation hugged a tight band. Where it wandered, later construction phases had shifted paving, but subsurface wall lines held the original azimuth. They then ran a simple water test, dye in a restored channel section. Flow stayed laminar at low volume, transitioned to controlled ripples at higher discharge right where a drop structure waited. Their note in the logbook was simple, planned for 2 seasons in 1 cut. One more layer people miss, defect handling. When subsidence cracked a platform corner, the repair used keyed stones and new plaster bands that feathered load back into the wall. You can read the triage in the masonry like a patient history. That's not stack rocks better. That's an engineering feedback loop. Bottom line, Teotihuacan looks like myth from a drone. On the ground, it reads like a standards manual you can walk. Once you see the measurement culture, the city stops being mysterious and starts being legible. Petra, Nabatean hydraulics, and desert-scale water control. You've seen cities tuned to stars and slopes. Now watch a civilization turn bare rock into a water computer. Petra isn't just facades, it's a hydraulics textbook carved into sandstone. The Nabateans didn't fight the desert, they domesticated it. Start with the channels. Along cliff walls and canyon bends, you'll find gutters cut with a consistency that's hard to appreciate until you measure gradient. Over hundreds of meters, the fall stays gentle, enough to keep water moving, not enough to tear channels apart in a flash flood. That's slope control across ranges of rock hardness and unpredictable head. Our checklist loves this. Metrology in fluid systems, grade sticks, plumbs, and level references had to be part of daily work. They didn't run raw runoff straight to the city. They filtered it. Settling basins sit upstream where silt drops out before clean water moves onward. In tight sections of the sick, channels duck behind carved baffles and undercut stone lids. Those lids do three jobs: keep debris out, limit evaporation, and stop animals from stepping in. If you see recurring lid widths and tongue and groove edges, that's standardization, jigs for shaping covers, and consistent wall rebates to accept them. Dimensional families across long runs, production pass. Pressure management is where Petra gets clever. Gravity gives head, head can burst joints. In limestone and sandstone, they cut pressure breaks, small cascades and vents to bleed spikes during storms. On longer lines, they used subtle siphons. Channels dip below a terrace, then rise, carrying flow over obstacles by maintaining a sealed column. You don't get a working siphon accidentally. You plan heights, seal joints, and align inlet and outlet levels to stay within the pressure you can tolerate before leaks. That's predictive math in rock. Look at cisterns, not as pits but as engineered lungs. Interior walls are coated with waterproof plasters, lime stabilized with ash or gypsum, smooth to reject seepage. Overflow lips sit at calibrated heights so one cistern spills to the next when storms overfill upstream capacity. That's timed release without a valve, geometry as a controller. You'll see intake screens, sediment sumps with cleanout niches, and access steps aligned to inspection routines. Workflow marks everywhere. Rough chiseled excavation below, plastered finish above, scribed level lines frozen mid-wall. Gradient accuracy is the quiet triumph. Over long traverses, channel floors maintain drop within tight bands. If the slope steepens briefly, a drop box resets head and restores a gentle grade. That pattern repeats, reset, run, reset like gear stages in fluid. The repeatability of these features across wadis closes our open loop again. Different crews, different dates, same solutions, same dimensions clustered around target numbers. Surplus logistics matter as much as scarcity. When rare cloudbursts turn wadis into battering rams, the system has sacrificial spillways and bypasses. Cut weirs step flood peaks into safe paths, protecting main conduits. Anti-silt strategies show up in plan. First basins catch, second polish, third store. Channels widen before turns to drop velocity, then narrow to resume flow. That's an energy budget you can sketch. Tooling signatures. In cut channels, parallel pick marks overrun and cleanup abrasion on floors point to a sequence. Rough to depth, true the bed with an abrasive loaded sled, then set covers. Cover stones bear repeated notch profiles, evidence of templates. Joint faces show slight burnish from lapping before setting mortar. That's stone metrology applied to water. Power in this system is gravity, multiplied by geometry and smoothed by mass. No mills required, just heads staged across a network. Materials are the usual suspects: limestone, sandstone, plaster, clay pipes in segments where rock couldn't be cut. And those pipes? Segment lengths cluster, joint bells repeat, wall thickness sits in a narrow range, mass production signals again. Repairs reuse the same sizes centuries later. Standards live because they solve headaches. Micro story. A civil team ran modern laser levels along a preserved sick channel segment. Over 420 meters, average slope sat near 0.5% with local resets at carved drops every 60-80 meters. They die-tested a restored branch, first clear flow, then they stirred a measured silt load upstream. Turbidity spikes hit the first basin and dropped by 2/3 before the second. The note in their log was crisp, designed for dirty first, clean later. Score it, precision, pass consistent gradients calibrated overflows. Power, pass gravity harnessed, pressure tamed. Materials, pass plasters, stone lids, ceramic segments. Metrology, strong pass, leveling practice writ everywhere. Production, pass standard lid widths, pipe segments, repeating joints. Predictive math, pass siphons, staged drops, overflow choreography. And here's the bridge. Petra proves measurement culture isn't just gears and flat stone. It's fluid set to a tempo with repeatable parts and planned failure modes. Hold that lens, because when we revisit Rome through it, the obvious infrastructure starts looking like precision machinery stretched across an empire. Roman industrialization, sawmills, watermills, and concrete. Hold the Petra lens over Rome and the picture sharpens fast. Everyone knows aqueducts and roads. Fewer people notice the machine logic linking quarries, mills, and concrete into a production line stretched across provinces. Rome didn't just build big, they built repeatably. Start with watermills. The Barbagal complex in southern Gaul is the poster child. A hillside packed with parallel mill runs, think 2 staircases of water wheels, about a dozen on each side, fed by a branch aqueduct. Gravity stages the head down each flight. Spill from one wheel becomes feed for the next. That's not rustic opportunism, it's power scheduling. Checklist time. Precision. Wheel housings and sluices had to hit consistent widths and drops or the chain stalls. Power pass with surplus. Hydraulic head times dozens of wheels is factory-scale torque. Materials, stone raceways, timber wheels, iron pins, standardized hardware. Metrology, tight because each drop sets the next. Production, parallelization by design. Predictive math, implicit in head budgeting and throughput calculations for grain. What did they do with all that torque? Grind, obviously, but the same water-to-rotary logic shows up in sawmills. The Hierapolis relief in modern Turkey depicts a crank and connecting rod driving a frame saw from a water wheel, rotary motion converted into reciprocation. That crank is a small detail with big consequences. Once you have it, you can mechanize linear feed tools. Stone saw frames become steady, rhythmic cutters. Paired with a simple ratchet or screw, you can advance the work at a controlled rate. Tool marks from Roman stone yards show straight, parallel kerfs that cluster in widths consistent with framed saws charged with abrasive. We saw the same signatures in Egypt. Here, water smooths the stroke and boosts repeatability. Rome's metrology hides in logistics. Survey gear, groma, corrubates, calibrated rods kept roads straight and aqueduct gradients shy but unbroken. A few millimeters per meter over tens of kilometers isn't vibe, it's bench logic on a landscape. At Pont du Gard, the channel bed falls so gently that the head at the city end arrives with calm flow. Deviate too steep and the water chews, too flat and it silts. Their solution is the Barbagal trick writ long: staged drops, settling basins, and maintenance access. A civil engineer would call it an error budget with reset points. Now add the chemistry that lets Roman process scale: pozzolanic concrete. Mix lime with volcanic ash, and you get a binder that sets underwater and gains strength over time as CaSH gels form. That unlocks harbor moles, pier foundations, and vaults that don't care about splash zones. It also standardizes formwork. Once your crew knows slump, mixed proportions, and cure windows, you can pour arches, channels, and floors to predictable behavior. The Pantheon dome isn't a miracle. It's material gradients tuned by density, heavy aggregate low, pumice light high, plus coffering to shave weight. That's predictive math in mixed design meeting geometry. Industrial hints keep piling up. The Army's standardized kit, nails, hinges, tent poles, even Caliga hobnails, points to scale production with gauged parts. In building, Tegula and Embrex roof tiles repeat so reliably that crews swap pieces without trimming. Brick stamps track batches and makers, which doubles as quality control. When you see brick courses stepped into concrete cores at regular lifts, you're looking at workflow marks: rough, then face, then finish, applied across cities. So sawmills again. With a crank, a connecting rod, and a frame, you can cut marble veneers with kerf widths that cluster in narrow bands. Blocks that would have eaten weeks of hand sawing now move through with steady feed and fewer blade wander issues. Water wheel inertia acts like a flywheel, smoothing torque ripples. If you stand in a Roman quarry and see saw cuts with consistent stroke spacing, you're reading cadence. Wheel RPM, crank radius, stroke length. That's machine rhythm frozen in stone. Survey instruments translate directly to production jigs. The corrubates, basically a long level with plumb lines, lets you set aqueduct beds within tight gradients. The groma's crossed arms give perpendiculars for road grids. Those instruments imply master rods and reference faces in wood and metal that rarely survive, but their outputs do. Straight causeways, rectangular castra whose gate widths repeat across continents, bridge arches whose radii land on rational geometries in plan after plan. Concrete changes workforce economics. With lime, ash, aggregate, and formwork, unskilled labor can pour to a master's line, while skilled hands set datums, check plumb, and true edges. That division of labor is a knowledge network. the foreman reading levels downstream of a surveyor, upstream of a mason setting brick faces, coordinated with a saw shop cutting veneer that will bed into the wet mortar. A city becomes a managed sequence. Run the checklist. Precision, gradients, kerf widths, arch geometries, pass. Power, water to rotary to reciprocation, pass. Materials, pozzolana concrete, seasoned timbers, iron fasteners, pass. Metrology, heavy pass, survey standards and layout logic everywhere. Production, hard pass, parallel mill lines, standardized tiles and bricks, army spec parts. Predictive math, pass, mixed design by density, crank kinematics, head budgets. Micro story. A team near Barbagal built a small water wheel, pinned a wooden crank, and rigged a frame saw with abrasive cord. They cut limestone blocks with a steady 90 strokes per minute. Their notes: stroke length 20 centimeters, feed rate about 0.3 millimeters per stroke, kerf width held within a tight band. Repeatability came from two things: constant head and a stiff frame. Translation: Rome's magic was fixtures and flow. Once you see Rome as parallelized power plus a chemistry toolkit, the empire reads like a distributed factory. Roads and rivers are conveyors, aqueducts are power buses, mills are engines, and concrete is the universal fixture that locks tolerances at scale. And that playbook, measure, mechanize, modularize, goes quiet in one place while it gets louder somewhere else. Islamic Golden Age, optics, astrolabes, and automata. Everything we've built so far, measurement, motion, materials, shows up again from Cordoba to Baghdad, but now with a new obsession: how light, time, and flow can be modeled, corrected, and displayed on demand. If Rome was parallel power, the Islamic Golden Age is precision as scholarship. Bench work tied to books, instruments tied to observatories, mechanisms tied to patrons who demanded results. Start with optics because it rewires the method. Most people think medieval optics is mirrors and mysticism. But according to Ibn al-Haytham's experiments, vision is light entering the eye, not rays shooting out. How do we know? He built test rigs, camera obscuras, slit experiments, controlled apertures. That's metrology for light. He isolated variables, predicted how images invert, and used geometry to quantify angles of incidence and reflection. Checklist hits: precision in aperture sizing and distances, predictive math in ray diagrams, materials in polished glass, burnished metal, and darkened chambers, production in repeated tests with documented setups, and metrology in calibrated baselines and measured angles. Power: gravity doesn't drive optics, disciplined method does. The takeaway is huge. An experimental culture standardizes not only tools but procedures. Now the astrolabe, the pocket analog computer of its day. Brass plates mater, interchangeable climate plates tympana for different latitudes, and a lacework reedy carrying star pointers over engraved coordinate grids. Rotate the reedy, set the altitude of a star or the sun, and it solves time, direction of prayer, and calendar problems in seconds. Those plates aren't scribbled. They're divided to minutes of arc with astonishing regularity. Workshops use dividers, pricked indices, and likely master templates to transfer scales. Some surviving astrolabes allow swapping plates between instruments and still reading true. That's interchangeability, our production signal, alive in metal. Precision: the engravings land on consistent spacing. The star positions match cataloged values within the expectations of the era. Materials: brass alloys that engrave cleanly and resist warp, wooden and leather cases to protect alignment, blued steel pointers for stiffness. Metrology: heavy pass, degree circles, azimuth lines, altitude arcs, and latitude-specific stereographic projections etched with repeatable structure. Predictive math. Off the charts, the projection transforms the dome of the sky to a plane so you can compute with rotation instead of trigonometry. You don't guess a stereographic grid. You construct it from geometric rules. Astrolabe shops were learning organizations. Inscriptions name makers, dates, and cities. Some carry correction notes, tiny deltas to star positions, evidence of updates as catalogs improved. Manuals teach users how to reduce errors, parallax advice, how to hold the alidade, where to sight. That's calibration culture passed to end users. And brass lathe techniques appear in bezels, boss pins, and concentricity of the mater. Faint but telling signs of controlled rotation in fabrication. Let's add automata because they expose the mechanical literacy behind the stagecraft. Al-Jazari, working in the 12th, 13th century, documents devices that sound like parlor tricks but run on crisp kinematics. Water clocks with float regulators, CAM-programmed musicians, hand-washing fountains with sequence control. The centerpiece is feedback like thinking. Take his elephant clock. A float in the belly drops at a controlled rate, pulling a line that advances a mechanism. When it hits a threshold, a reset triggers. Balls drop, doors open, a bird chirps, and the system re-zeros for another cycle. That's state management. In other clocks, he uses a clepsydra feeding a scoop wheel that releases notches at near constant intervals, proto-escapement logic paired with water head smoothing. Tooling signatures come through his drawings: pins, collars, keys, and cams with defined profiles. Cams aren't random, their lobes encode timing curves. If you've ever filed a cam by hand, you know drift ruins performance. Al-Jazari's instructions specify radii, offsets, and assembly sequences that minimize stack-up error. Materials: bronze bushings, hardwood frames, finely stitched leather seals, and carefully sized pipes to tame head fluctuations. Production: patrons demanded reliability for court displays, so workshops standardized pin diameters, reused bucket sizes, and kept spares. His book reads like a service manual: how to align, oil, and troubleshoot. Observatories scale the culture up. Maragha and later Samarkand deploy mural sextants, armillary spheres, and giant quadrants. Stone and plaster arcs carry degree marks over several meters. The sheer size reduces random error. You see survey logic again. Set a reference meridian, true the instrument to plumb, check against standard stars, log corrections. This marries predictive math, refining planetary models, to metrology, averaging repeated measures, estimating instrument error, publishing ZIJ tables with stated precision. The knowledge network is explicit. Translations from Greek, Indian, and Persian sources feed designs. New results feed back as improved tables, better astrolabe plates, and refined prayer time algorithms. Run the checklist cleanly. Precision: angular divisions to fine increments on brass and stone. Concentricity and flatness in rotating plates pass. Power: waterhead driving regulators, counterweights, floats pass with smoothing. Materials: brass metallurgy, timber craft, leather hydraulics, polished optics pass. Metrology: heavy pass, degree standards, calibration rituals, manuals. Production: pass, interchangeable tympana, standardized pins, repeatable clock modules. Predictive math: hard pass, stereographic projection, trigonometric tables, cam timing, and feedback cycles. Micro story: a modern instrument maker reproduced a 10-inch astrolabe strictly by Al-Khwarizmi era instructions and tools: dividers, scribing needles, scraping gravers. First try, his reedy bound on the plate, warped just enough to scrape. Second build, he normalized the brass, annealed between steps, and re-indexed the degree circle with a punched guide plate. The reedy spun freely, star alignments matched within a few minutes of arc. His comment was simple: the trick isn't the cut, it's the order of operations. Here's why this era matters to our pattern. They don't just build clever things, they trap error. Written procedures, calibration rituals, interchangeable parts, and feedback mechanisms show a culture that expects drift and designs against it. That's the same logic you saw in Greek ratios, Egyptian stone planes, Indian retorts, Chinese escapements, and Roman head budgets, now fused with explicit experiment and documentation. When measurement culture writes its own handbook, precision stops being accidental and starts being policy. The pattern: metrology, power, and knowledge networks. Okay, so here's the thing most people miss. The artifacts aren't the point. The pattern behind them is. Across Greece, Egypt, India, China, Mesoamerica, Petra, Rome, and the Islamic workshops, three threads keep weaving through the evidence: metrology, power, and networks of people who kept the tricks alive long enough to scale them. Start with metrology because nothing else holds without it. Every culture that punched above its apparent toolset built a habit of reference. Greeks indexed gear teeth and dial marks, Egyptians trued planes and kept feed rates steady, Indians standardized retorts and crucibles, Chinese divided circles and ticked water into time, Teotihuacan held azimuth for kilometers, Nabateans locked gradients over canyons, Romans froze slopes in aqueduct beds and kerf widths in mills, and Islamic shops engraved degree lines you could trust in the dark. Different materials, same reflex. Pick a datum, then defend it against drift with procedures, templates, and checks. That's why repeatability is the one measurement that collapses the debate. If a result lands inside the same narrow band again and again, across teams, sites, and years, you're looking at a system, not a miracle. Now power, not electricity, energy you can meter and smooth. Heavy frames store inertia and make human hands act like a motor. Waterhead turns chaotic flow into regulated torque. Gravity does downforce so muscles don't have to improvise it. Heat in furnaces becomes predictable when you trap it in retort banks and throttle air with draft geometry. Even a hand crank, when paired with bushings, oil, and balanced wheels, becomes a stable source of rotation. Everywhere the pattern shows up, power isn't just bigger, it's buffered. Flywheels, head tanks, staged drops, weighted laps, counterweights, floats. These are analog filters on noisy inputs. Precision is the child of smoothed energy. But none of this survives without knowledge networks. A one-off genius doesn't give you clustered kerf widths, interchangeable astrolabe plates, or retorts by the thousand. Workshops do. Guilds, court bureaus, patron-funded benches, army supply depots, quarry camps, barrio economies. These are the memory cells of a civilization. They store master patterns, train apprentices in the order of operations, and write the little rules that kill error before it kills output. You can see the network in signatures. The same pin diameters showing up across instruments, the same lid rebates repeating across Petra's channels, the same brick stamps pacing a province, the same stereographic grids traveling across centuries because the math rides in the metal. But here's where it gets interesting. The pattern also exposes the bottlenecks. Energy density stayed low, so people built fixtures to multiply control instead of chasing raw power. Materials were perishable, so the most important parts of the system, wooden jigs, leather seals, master rods, templates, vanished, leaving only their shadows in surfaces and dimensions. Literacy wasn't universal. So method lived in routines and orally transmitted steps, which makes it fragile in wars, fires, and political swings. When the network breaks, the metrology dies first, not because the idea disappears, but because the reference artifacts do. Everything changes when you realize the same solutions recur. Differentials appear in Greece and China. Escapement logic shows up in clepsydras and tower clocks. Hydraulic regulation looks the same from Petra to Rome. Abrasive lapping turns granite and diorite into flats by the same slow truth. Weight, stroke, pigment check, repeat. Stereographic projection in astrolabes rhymes with gearing ratios in the Antikythera. Different math, same logic. Transform a hard problem into a rotation you can count. The recurrence isn't coincidence, it's convergent engineering under constraints. Remember our open loop from the start? Repeatability. Here's the payoff. If an artifact class, gear module, kerf width, retort diameter, cistern overflow lip, clusters tightly across sites, you have a measurement culture. Period. It doesn't matter if the tools were copper, bronze, iron, or hardwood. It doesn't matter if the power was a bow drill, a water wheel, or 10 people walking a frame saw. Repeatability is the signature of standards enforced by habit, checked by tools, and taught by networks. So what do you do with a pattern like that? You stop asking, could they? And start asking, where's the bench? Look for the fixtures in negative. If you see consistent bore diameters, expect bushings and reamers. If you see long, true flats, expect surface plates and straight edges. If gradients hold across terrain, expect level staffs, string lines, and sighting routines. If star positions line up on brass, expect dividing plates, templates, and anneal steps to manage warp. If zinc condensed by the ton, expect retort molds, firing schedules, and a kiln layout that doubles as process control. Once you understand this, the skeptic's playbook shrinks. Skilled hands, no machines is true but incomplete. Skilled hands plus jigs plus smooth power equals machines in all but name. Abrasive slurry explains everything collapses unless you show how feed, pressure, and alignment were stabilized. Isolated genius falls apart in the face of dimensional families and service manuals. Ritual objects can still be ritual, but ritual built by industrial logistics. The last piece is humility. We're good at building big and fast with high-energy tools. They were good at building steady with low-energy fixtures. Two different answers to the same equation. How do you get matter to obey? The artifacts we've walked through answer with the same three words: measure, buffer, share. You can erase a library. You can burn a workshop. But the pattern tends to reappear because it's the shortest path from a human hand to a reliable result. Skeptics Corner, natural explanations versus the checklist. Let's put the friendly version away and argue like adults. The safest story is always skilled artisans, no machines. I agree with half of it. Skill is everywhere. But our checklist isn't asking for drama, it's asking for tolerances and repeatability. When you get uniform helical striation pitched down a granite core, you're not seeing random excellence. You're seeing feed per revolution behaving like a controlled variable. Skilled hands often invent guides because guides lower error. That's a machine in everything but the motor. Next claim, abrasive slurry explains everything. Abrasives explain cutting. They don't explain consistent kerf widths over meters or repeated bore diameters clustered in families across sites or parallelism that holds within tiny angular bands. Slurry without controlled downforce, straight guidance, and steady stroke gives you wandering marks and taper. The moment the marks show steady pitch or constant width, the burden shifts. What stabilized motion? Weighted frames, jigs, or regulated drives fit the data better than freehand persistence. Then there's isolated geniuses. Sure, Eratosthenes measures Earth, Archimedes writes on levers, Susong builds a tower clock, Al-Jazari documents cams. But isolated genius doesn't yield clustered dimensions in tool marks, interchangeable tympano in astrolabes, or retort banks by the thousand. Those are workshop signatures across decades. Our checklist looks for metrology footprints, reference faces, dividing practices, datum habits. When they repeat, you're staring at a training pipeline, not a single bright candle in a dark room. Ritual objects is the catch-all. Everything may be ritual to someone, but fabrication realities don't care about incense. If a lid seats on a high-area contact with even pressure bands, that's a functional interface. If channel gradients hug a narrow slope over kilometers, that's hydraulic control. If city axes hit astronomical events consistently, that's a calendar regulator. Ceremony can ride on engineering, but it can't produce engineering signatures by coincidence at scale. Copper can't cut granite. Correct, copper carrying quartz or corundum can. That's how lapidary has worked for millennia. The question is what's harder? It's what carries the abrasive and how is the force applied? The tool marks point to tubular carriers, framed saws, and lapped flats. When diameters and kerfs cluster, the carriers were standardized. When faces are trued, reference plates existed, even if they rotted. Watermills didn't exist there, so no power. Irrelevant dodge. Our checklist never demanded a turbine under every quarry. You can smooth energy with mass, heavy frames, sled laps, counterweights, flywheel wheels. You can regulate feed with jigs and screws. Where watermills appear, Barbagal, Hierapolis, the stroke signatures get steadier. Where they don't, the signatures still show guided motion, just with human power buffered by fixtures. Batteries prove electricity. Slow down. The jar copper iron stack can generate voltage in replica tests, yes. But the production signals banks wired in series, plating defects across many artifacts, residue maps, are thin to absent. Our verdict landed conservative, plausible proto-electrochemistry, industrial use unproven. That's the checklist doing its job both ways. What about confirmation bias? You're reading machines into scratches. Fair. That's why repeatability is the open loop we closed. One artifact can mislead. Families of measurements across contexts forming tight clusters are harder to hand-wave. When gear tooth counts, kerf widths, bore diameters, slope gradients, and plate divisions pile into bands, the simplest explanation is standards. Standards require metrology, training, and fixtures. Why don't we find the tools? We do sometimes: bows, drills, lathes, water wheels, astrolabe shops. But the most critical pieces are perishable: wooden frames, leather seals, cord abrasives, master rods. Those vanish first. What survives are their shadows, the geometry they enforced. Archaeology is full of negative space. The checklist was built to read it. What we still can't explain cleanly? A few surfaces in hard stone push past what casual reconstructions can duplicate in time and scale with strictly unassisted freehand. Some Mesoamerican acoustic effects may be emergent rather than engineered. The exact escapement details in early Chinese clocks remain debated in reconstructions. And yes, the Antikythera's workshop ecosystem is inferred from inscriptions and parallels, not a found factory floor. We label those as open. And what can we explain? Predictive machinery in Greece by gear count, inscription, and function. Repeatable drilling and sawing regimes in Egypt by marked geometry. Corrosion performance in India by composition and passive film microchemistry. Zinc distillation by retort fields and residues. Differential logic in Chinese vehicles by mechanism. Hydraulic regulation at Petra by gradients, resets, and lids. Roman crank rod saws by relief, kinematics, and kerfs. Islamic metrology by engraved divisions, manuals, and observatories. So the natural explanations aren't wrong, they're incomplete. Skilled hands becomes skilled hands plus fixtures. Abrasive slurry becomes abrasive slurry plus feed control. Ritual becomes ritual plus logistics. The checklist forces the upgrade. When the marks, ratios, and repeats say process, the burden of proof moves off miracle and onto method. Erasure, bottlenecks, and the fragility of tech memory. So if the pattern is real, why does it keep vanishing? Short answer: the bench is mortal. The tools that enforce standards, straight edges, templates, jigs, dividing plates, tend to be wood, leather, cord, and glue. Stone and bronze survive, reference gear rots. When a workshop burns or a guild is scattered, you don't just lose buildings, you lose the calibration lineage. The next generation inherits monuments, not methods. Catastrophes break chains fast. Fires erase manuals in a night. Invasions dissolve patronage networks that funded instrument shops. Plagues target masters and foremen, the people who know order of operations by heart. A clock tower without its caretaker is a sculpture. An aqueduct without its maintenance crews is a landslide waiting for rain. The weakest link is always the human network that keeps the error budget in check. Gatekeeping slows time even when nobody's invading. Priesthoods, courts, and guilds hoard recipes because scarcity equals power. You see it with Woot's charged secrets, astrolabe shops that guard dividing tricks and retort clay mixes treated like family heirlooms. That works until the line ends. One silent apprentice intake, one famine, one purge, and decades of tacit knowledge evaporate. A method without a market is a rumor. Material decay biases the record. Leather seals, cord-abrasive rigs, wooden frames, waxed cords with carefully spaced knots, all gone. What's left are their shadows. Flat planes that demand surface plates, curved clusters that imply framed saws, concentric plates that whisper lathes. Skeptics point at the absence of tools. They miss that the tool's essence is encoded in the geometry it enforces. Archaeology is negative space science. Literacy gaps add drift. When procedures live in hands, not pages, you need continuous practice to keep tolerances tight. Marginal notes in a treatise, anneal between divisions, keep head constant, matter more than grand theory. Lose the margin, keep the theory, and you keep building pretty but unstable machines. That's how an astrolabe becomes a talisman and a water clock becomes a fountain. Geography decides who forgets and who remembers. Centers of empire attract talent and money, but they're also where fires, coups, and reformers swing hardest. Peripheries, back valleys, provincial towns, diaspora communities quietly keep the old fixtures running because they have to. That's why you find late-use retort molds away from capitals or conservative gear styles lingering in remote workshops. The edge shelters the bench while the center resets the fashion. Energy bottlenecks preserve fragility. Low energy density forces reliance on fixtures and disciplined teams. That's robust against a broken belt but brittle against missing people. Replace a water wheel, you're fine. Lose the person who knows how to balance a frame saw and tune its feed, production craters. High-energy eras swap that dependence, more power, fewer hands. But when fuel chains break, big systems stall too. Different fragility, same root cause. The bench is a social graph. There's also prestige drift. Patrons shift tastes. A court that used to fund observatories decides to fund gardens. A city that once paid for survey parties diverts to pageants. Instruments become display pieces instead of tools. You can feel the decay in inscriptions. Dates and maker names remain. Calibration notes thin out. The output still looks gorgeous, but the metrology has left the building. Micro story. A restoration team inherited a 17th century quadrant's fragments. The frame was intact. The plumb bob was gone. They reconstructed the bob to weight and length, but readings wandered. An old note surfaced later. Oil the thread. Capillarity damped swing, steadied the zero, and halved the noise. One forgotten sentence was the difference between Dacre and data. What's the fix? Redundancy and openness. Multiple copies of standards in different places. Public procedures, not private recipes. Durable reference artifacts, stone and metal plates that outlive the shop that made them. Apprenticeship trees mapped on paper so a plague doesn't wipe an entire branch. And yes, archives with methods and mistakes, not just triumphs. When you document your error budget, you bequeath resilience. Because here's the uncomfortable truth. The past didn't lose miracles, it lost manuals. And a civilization's real technology isn't the artifact. It's the habit of measurement, the fixtures that tame energy, and the network that teaches the order of operations. Cut that web and precision collapses in a generation. Keep it, and even low-energy tools punch far above their weight. The test bench, how to verify ancient precision today. Okay, so we've argued the pattern. Now let's put it on a bench and stop guessing. If we want this debate to move, we need tests that are cheap, repeatable, and public. Here's the toolkit and exactly how to use it. First, non-destructive metrology. Start with high-resolution 3D scanning, structured light or laser, to capture surfaces at sub-millimeter or where allowed tens of microns. You're not just making pretty meshes, you're extracting planes, radii, and angles. Then pull surface profiles, run line roughness, RAW/RZ, waviness, and curvature maps across long cuts. That tells you if a face was lapped, scraped, or simply dressed with percussion. Add reflectance transformation imaging for low-relief tool marks, spiral striations in cores, saw kerf chatter, lapping strokes. The goal is to turn "this looks flat" into "this plane holds within" 0.5 degrees over 1.5 meters with directional micro-scratch alignment. Next, microstructure and residues, but with a scalpel, not a chisel. Use handheld XRF for alloy fingerprints on the spot. Brass versus bronze, lead content, zinc gradients across a plated suspect. Follow with portable Raman FTIR to read mineral phases in abrasive residues, quartz versus corundum versus emery on cut faces. Where curators allow micro-sampling, we're talking specs, polish cross-sections, and hit them with SEM EDS. That resolves passive films on iron, cementite networks in crucible steel, vitrification stages in retorts, and zinc oxide condensation signatures versus random soot. You want phase diagrams anchored to real spectra, not vibes. Now the part everyone fights over, experimental archaeology with constraints. That means period-credible tools, documented steps, and hard success criteria. No, we eyeballed it and it looked right. Define tolerances before you start. Plane flatness within X microns over Y length, bore roundness within Z, kerf width variance within N%, gradient held to plus or minus mm time, and manpower must be logged. If you need a modern bearing to keep a rig alive, say so. Better, design a wooden or bronze bushing that matches survivable signatures. The test isn't can one artisan do it once. It's can a team hit the same band 3 times running. Replication criteria need 4 columns. Dimensional, flatness, parallelism, squareness, roundness, pitch of striations. Process, tool materials, abrasive grain, feed force, stroke frequency, cooling, lubrication. Throughput, rate per hour, failure rates, e.g., retorts cracking and rework. Scalability, jigs, fixtures required, and whether those leave detectable marks. If your reproduction uses a jig, perfect. The jig is the point. Describe it. Better, instrument it. Stick a load cell under the weighted lap. Put a tack on the bow, drill, or water wheel. Log feed per stroke with a dial or a scribed ruler. Publish the error budget, where the build drifted, what fixed it, and which step was sensitive to order of operations. We also need site-scale metrology, because a lot of the precision lives in grids and gradients. Fly LiDAR over urban plans, but don't stop at the pretty cloud. Fit best line azimuths to avenues, calculate standard deviations by construction phase, and correlate deviations with subsurface wall lines to separate original datums from later repairs. In channels, run differential GPS or laser levels over long runs, then compute slope histograms and identify reset structures. If gradients cluster around tight means with ritual resets, you're looking at a hydraulic standard, not a happy accident. Public datasets are the only way this stops being a personality contest. For every scan, dump. Raw and decimated meshes, with metadata on scanner, resolution, noise. Tool mark vector fields, direction and density, surface roughness tracks, profile lines with stationing. Spectra from XRF Raman FTIR, SEM with calibration standards listed. Replication logs, materials, grain size distributions, mass of weights, stroke rates, temperatures, time to failure, and photos, video of setups. Statistical summaries, distributions not cherry-pick best cases, show the misses. Make it boringly transparent. Put it on an open repo with version data. Require a methods in 10 steps sheet for each test so a grad team in another country can rerun it without guessing. If a museum can't release full meshes, publish derived metrics with documented pipelines so results are comparable. 2 fast case packages, I'd green light tomorrow. Granite core study, pick 3 cores with clear spirals. Scan interiors, unwrap to cylindrical coordinates and extract striation pitch versus depth. Replicate with copper tube plus quartz slurry rigs at controlled feed. Vary only 1 parameter per run, abrasive grain, feed weight, rotation rate. Publish where the pitch stabilizes and where it wanders. Verdict rides on whether field pitches fall inside the repeat band of a guided rig. Petra channel gradient run. Select a continuous 500 m segment with covers present. Shoot elevations every 5 m. Identify drop boxes and compute slope segments. Build a 110 scale flume with the same reset pattern and run dyed flow at 2 discharge regimes with sediment added. If the model reproduces transition points and sediment traps without tuning each feature, you've validated the design logic. One more, astrolabe division repeatability. Scan 3 historic plates from different makers, fit their stereographic grids, and measure deviation from ideal. Then have 2 independent shops reproduce plates by period methods and tools. Compare deviation fields. If the old plates beat or match modern replicas built under the same constraints, the metrology claim stands, and we learn the order of operations that matters most. Last thing, pre-register the question. Before any test, write the acceptance criterion that would count as a pass for the ancient method versus a fail requiring unseen fixtures or power. That keeps us honest. If results break your hypothesis, publish anyway. Negative results are gold. They prune fantasy. Bottom line, stop arguing in adjectives. Scan, profile, replicate under constraints, and publish the distributions. If the artifacts live inside narrow bands we can reproduce with documented rigs, the impossible becomes a syllabus. If they don't, we'll know which missing fixtures to hunt. We started with a simple claim. Repeatability collapses the debate. After everything you've seen, gears that predict eclipses, stone that remembers motion, metals that encode process, cities that hold their line for kilometers, the pattern isn't a mystery. It's a habit. Measure, buffer, share. That's why these artifacts still hit you in the gut. They're not just objects. They're the fingerprints of people who learned how to trap error and pass that skill along. The tools rotted. The habits survived in the surfaces. So here's what happens next. We're taking this out of theory and onto the bench. In the next video, we'll run a head-to-head replication under constraints and publish the distributions. No adjectives, just data. Pick the first target. Granite core striation, pitch versus feed per rev with copper tube plus quartz slurry. Guided versus freehand. Petra channel gradient control at scale, with stage drops in a 110 flume. Astrolabe plate division accuracy, using period tools and annealing steps. Roman crank rod frame saw cadence mapped to kerf signatures. Drop your vote and your reasoning in the comments. We'll pre-register the acceptance criteria before we start, film the full process, and release the raw scans and logs so anyone can rerun it. If you want a seat on the shop floor when the numbers land, subscribe and turn on notifications. The next episode is the moment the pattern proves itself, or breaks. Either way, you'll see it, measure it, and know.